Okay, let us get started. I apologize, I'm emceeing remotely from Chicago, getting ready for the SFN meeting, and I'm a slightly noisy environment, but with those apologies, it is my huge pleasure to welcome this month's speaker, Mike Milham. Mike is the Chief Science Officer and the founding director of the Center for the Developing Brain. He is the director of the Healthy Brain Network, and he's a senior child and adolescent psychiatrist at the Child Mind Institute. Mike has been I call him one of the godfathers of the Open Science Initiative and led certainly some of the earliest grassroots data sharing efforts, 1,000 functional connectomes, leading that off, and then followed up by many groundbreaking initiatives. So there's so many things, Mike works with us on and near us on, and is a leader in, so it's just a fabulous opportunity to have him present at today's webinar. So I guess without further ado, I will turn the floor over to Mike.
Yeah, thank you. And the Godfather reference probably goes well with the voice I got today. But it's a pleasure to be speaking today, and it was interesting. So I will say today I'm going to be a little more focused than I usually am in most talks, but nevertheless, I guess I'm not as much. But I'm going to focus heavily on a particular work that that came out this past year that really sunk a number of years of our effort, which I think had good value for why we did it. And I think there's a good number of learning lessons along the way that go way beyond the specifics of what we dealt with. So with that said, let me just okay, my screen is changing. Okay, great. So this is the last crowd in the world I need to worry about pointing out the challenges of reproducibility. And, it's the standard pieces we all discuss. How do we bring about reproducibility? We have so many data processing pipelines. How do you deal with lack of consensus on standards? Whether it be talking about processing steps, quality assurance, any of the very pieces. How do you deal with things that look like they're similar, but actually could yield quite differing results? And there's just a whole slew of papers where people either giving similar challenges or similar components and wind up finding out that they can have results that are quite different. And there's so many lessons to be learned. And also how to get folks to actually care. That's a really hard one. It's not glorious work at all. So when you are taking on issues like trying to understand pipeline variation in particular, it often closes a lot of people's ears immediately. And so how do we do that? How do we go about this? So I will say this work actually started in about 2019. Ted Satterthwaite and myself had gotten a grant where we're going to do is take 7 sites worth of data that would be upwards of 7,000 to 10,000 data sets. And we were going to work on harmonizing the imaging and the phenotyping. And quickly, something that's actually now released in its early form called the Reproducible Brain Chart Project. But one of the first things was whose pipeline are we using and who's handling the sharing, what standards, all those questions immediately arose. At the time, I said, well, why wouldn't we use CPAC? Ted, of course, has XCP. So he's like, why wouldn't we use XCP? And that's feeding off of fMRI prep. And then quickly, came the conversation of, well, are they really so different? And anything that's different in one, why can't I get a configurable pipeline? Why can't I increase configurability to be able to bridge the gap from one pipeline to the next? And that, I was like, this will take a few months. So that started in 2019. I would say the first round of it probably finished in like 2021. The Reproducible Brain Chart Project, Ted and I, something that we said we would release data in the first 6 months. It was like 4 years later by the time we dealt with the many different fronts of what to obsess about. And that's with us arguing that we should move fast on things. So, that's the nature of these challenges. But here it really was, in all these conversations, we spent so much time talking about global signal regression and all these pieces. And we couldn't even get ourselves as 2 people who collaborate together and work together to agree on minimal pre-processing steps. Just literally the base minimal pre-processing. So that spawned this question. doesn't matter. Because whenever you spend a lot of time arguing about things in academics, you always have to get that other piece of doesn't matter. Is it impactful? Why should anyone care? And so from that came, and most of what I'm talking about, you can easily find in this paper. Is published earlier this year in Nature Human Behavior. But it comes down to how do we evaluate, and how do we figure out whether or not we should care? So coming from someone from the medical world, you immediately think of, well, these are two different raters. So let's think about inter-rater reliability. But I'm going to start off with a digression about reliability, because I think one of the things that we see is there's just a number of different conceptions of whether or not we should care about reliability and what reliability is. And I will warn you, my voice, I can tell you, is going to vary a lot in this, so please forgive it. Okay, so first of all, why do we focus on reliability? And this is something I can tell you in the review process with this paper and a few others. We were surprised by the amount of pushback we got over why are you focusing on reliability? And folks often point to this paper, beyond fingerprinting, choosing predictive connectomes over reliable connectomes, where people could say, well, maybe focusing on reliability is not the right idea. Maybe you should just focus on predictive validity. And I think this here, and I don't think the authors here really intended some of the implications this paper has had in people's minds, but it's not a choose one kind of situation. In order to understand why I say that, we could just go back to the basics. Biomarkers. Anytime you look at biomarkers, you want to talk about individual differences or anything along those lines. You would talk about validity, reliability, sensitivity, and specificity. These are the 4 hallmarks. I don't think anyone would disagree. Any laboratory test requires these 4. So from that perspective, if we choose just one, we can fail. So if we choose just validity, but we don't have reliability or vice versa, someone could say, so which one should you choose? Well, for that, and this goes back to work that we published some years ago with Sinyan Zuo and Ting Zhu, where we just try to drive home an obvious reality, which is when we talk about reliability, the reason why we focus so much about reliability is it provides an upper bound on validity. So you can't be more valid than you are reliable. So one can say, okay, but you can be reliable and not valid, and that's 100% true. So you can sit there and have something that's reliable, but it's being driven by noise. But what you can have is something that's valid, but not reliable. By that definitionally, you run into a problem. So the way we approach this is we think about optimizing reliability because of the fact that it is the upper bound. At the same time, you want to complement things where you don't want to only think about reliability. You have to, in the field, think about validity as well. But as far as the first step, reliability is a leading edge in our minds. And it matters a lot, and this we tried to point out years ago, because folks really put an emphasis on large scale samples. And look, we've done that for years. We've argued data sharing. The big value in so many ways is aggregating large scale samples. But there's a confusion as to what end. It's really important in our mind, at least, to understand that you're talking about a trade-off between sample size and reliability. So when your data is low reliability, then you need much larger samples to appreciate the same effect, which when you think about that, it goes against the value, it diminishes the value of large scale data. If large scale data is just about trying to sit there and make up for a factor using low reliability data, it's helpful, arguably, but it misses the real value, which is about appreciating heterogeneity in samples. About whenever you hear about people talking about biomarker discovery and the varying forms of autism and ADHD and the different things we want to derive from the brain, you can't do that if you're wasting large scale samples on trying to make up for having not acquired reliable data or using reliable tools. And this is a point that we've tried to drive home is there's the issue of when you talk about reliability, it's a critical for any sort of laboratory biomarker discovery. It is an upper bound on validity. It's also challenging because you have a field where reliability itself could be, there's a growing number of measures people use to try to assess reliability. And part of the challenge is, there's the most classic being interclass correlation coefficient. But that's a parametric measure, and that's also typically conceptualized in univariate sense. So what happens now when you're dealing with imaging, where you're dealing with something very multivariate? And over the years, you've seen things like there's I2B2, which is one extension. There's also a distance-based ICC that's been developed. Again, both parametric. There's discriminability, which has been developed as a non-parametric, and that really builds off of identification rate or fingerprinting. And, the idea is, so you have a few challenges here. We're chasing after data that we know must be reliable. We have to acknowledge that reliability is a prerequisite for validity. We have the challenges of which measure to use to assess reliability. Do you want to use the univariate situation where, from that perspective, you're then looking at individual connections, or when you're talking about functional connectomics, you're going to want to think about the full connectivity matrix. And and then how do you build tools? And here's like an example, one from Tingzhu, really to help try to even think through questions of optimization, where you then have to think about like your between subject variation, your within subject variation, and when you're trying to figure out what to optimize, for a given data set in different situation, optimizing one versus the other may give you differing results as far as how much yield you get in reliability. So the point is, it's a critical component for thinking. And when we approach pipeline-related variation, this is where our mindset comes from. And we've spent years worrying about this, reliability being the bottleneck. And here's one paper, a commentary we did some years ago, where we really tried to drive home, like it really is a bottleneck. And when you look at the sources of bottleneck, it could be the data. So is the data reliable enough? It could be the pipelines that we're dealing with. And and then it also could be the other side of the equation. It could be the phenotypic data. It could be nothing. Let's say you have perfect imaging and perfect genetics or whatever, and it's perfectly measured. What about the behavior relating it to? So we keep trying to go back and get folks to think about the complexity of the challenge at hand, and that really the bottleneck that lives in reliability is not the only bottleneck, but in our minds, it's an undeniable one. And the field has been seeing this over the years. You've seen a growing number of studies worrying about test-retest reliability. We had done one of the first test-retest reliabilities, the Shahzad et al. Paper back in 2009, where we were happy with what we saw because we had the default network and frontal parietal network. And a certain number of years, what became obvious is those are the two most reliable networks. Look at some other networks and you'll be less happy. And that comes into, a range of papers over the years that really have highlighted the way to get past this is by increasing the amount of data. And here's two papers from the late 2000s. Here's 2017, 2019. The one on the left is from us. The one on the right is from Max Elliott, where, the common finding is go from 10 to 20 to 30 minutes of data, and you see really dramatic changes in the reliability of your data. And that coincides with a lot of Tim Lauman's work when he was helping use Russ Poldrak's My Connectome project and drive home that focus. So, this here has always been in our head, the data perspective. And this is where we started. And here's a paper of Seok-Jun Hong, where here using gradients, using them as biomarkers, and again, appreciating the value of going from 10 to 20 to 30 to 50 minutes of data. But all this is talking about the data. One last one here. This is a little bit of a twist. This was some work from Yufeng Zhang looking at inter versus intra scanner. So now not just thinking about test retest, but data acquired on differing scanners versus the same scanner on different occasions. This puts us more towards the tool, but this is an acquisition tool. So the thing is, let's say that we've learned enough now to know what it takes to get highly reliable data. And anyone who's been pushing the idea of precision fMRI, which I may not love the name, but the bottom line is what they're arguing about is get high quantities of data on an individual to make it more reliable. Yes, that's true. And you can do quite well. There's also potential optimizations like using multi-echo. Connor Liston's team showed the value of multi-echo data in having much higher reliability than more traditional EPI approaches. And so maybe in Connor's world, his argument would be use multi-echo as a way of requiring notably less data. But the bottom line is whether you need more data or different protocols or both, it's an eminently solvable problem in my mind as far as taking on the reliability challenge with imaging data from the data perspective. We might not always like the solutions, but they exist. But then that brings us to the pipelines. So the pipelines, when we looked at this, we, of course, started with arguments about global signal versus not, and who wants to do an ICOR, and who wants 12 parameters versus 24 parameters versus 36 parameters for motion correction and all these things. But when we went back and just started with the very basic pieces, that is, let's take the minimal pre-processing elements and say, do they matter? So for the purposes of this, something that initially grew with a smaller conversation, we started reaching out to the differing teams. So we wound up with 5 pipelines. The ABCD bids from Damien Fair's team, the Connectome computational systems, Tingzhu and Sinyan Zuo, CPAC, which is the platform that we're using in-house, DPARS, Chao Ganyan, and fMRI Prep. And what we wound up saying is, what if we took the same data and put it through each of these pipelines and asked the reliability question? And what if we did it with a data set like the Hangzhou Normal University data set that was part of the core, the Consortium for Reliability and Reproducibility Initiative, where it was 29 subjects that were each scanned for 10 minutes across each of 10 sessions. It opens up possibilities. We can start asking questions about taking the same subject, same data, and putting it through different pipelines versus same subject, different time point, and putting that through different pipelines. Let's figure out what matters and what doesn't. So a lot of arguments we were having among ourselves, we could just get answers. And then in that process, figure out the differences, anything that matters. From the CPAC perspective, I was like, this will be easy. We'll just add configurability so that we could emulate the other package and everyone would move on. And I was like, this will take a matter of a few months. So one of the first things we did is we looked at the different pipelines and we said, okay, everyone's minimal pre-processing. And here what you're seeing is at the highest level, they all look pretty similar. Everyone's denoising, brain extraction, tissue segmentation, anatomical registration, slice timing correction, motion estimation, bold mass generation, despiking, co-registration. Should be easy. But then you take a look, and in each package, you do see variation in what specific tools are being used. And I would like to say this is as complex as it gets, but anyone who's actually tried doing this would tell you that even when we have the same routine in 2 different packages, the way they're glued together or the little tweaks are quite profound. The funniest part is trying to get teams to actually be able to put this together, because the first thing we started noticing is what our team calls pre-processing and another team calls post-processing. But everyone has wound up finding out and these are all collaborators, we're all friends, we work together, we collaborate together. Our teams all had fairly different vocabularies that were being used to discuss the different steps in the processing pipelines. And here, this one here tries to take a look at conceptual differences. This is one of the supplementary figures in the paper. Same approach, same objective, different approach, same objective, different approach, different objectives. And we really tried to figure out ways of figuring out conceptually which pipelines are more or less far apart. The most obvious one is dparfs. With respect to the fact that dparfs is MATLAB based, at least the version we used. On the flip side, Xiao Ganyan worked with me for some years and was here when we were creating CPAC, and so a lot of the thinking in CPAC and dparfs has a lot of overlap. So you get into all these different questions. So what happens when we took on the first challenge? Well, the first thing we did is got into the disagreements over what measure of reliability. So the answer was, let's do multiple. Let's say first, within subject, we're going to get the connectivity matrix and just say, correlate this matrix with this matrix. And so that one there gives us a spatial correlation number for each subject. Then comes, well, fine, let's think about ICC. So now you're going to go edge by edge and talk about individual differences and say how reliable are individual differences at every edge in your connectome. And then comes the multivariate perspective. And of course, do you want parametric or non-parametric? We said, fine, do both. And so we have I2C2 and discriminability. And then, of course, what representation you're going to use. So we said, fine, take the Schiffer atlas. We'll do 200, 600, and 1,000, and hope it all just doesn't matter. So, of course, what do you wind up finding out? You wind up finding out in your ideal, keep in mind, what you're seeing is pipeline A and pipeline B. So there's the same exact data sets going to each of the two pipelines. So everything should be like one in our ideal world. I remember Russ Poldrak on one of the calls where we were all agreeing on the analyses and everything. I was like, Russ, what would make you feel good? He's like 0.8 or higher. So, okay, there's 0.8. So 0.8 is the less conservative number. 0.9 is the more conservative number you'll see in literature. 1 is your ideal. So then comes your obvious. These pipelines, which are conceptually similar, are not looking so similar when we've given the same exact data. So what does that mean? Well, that means that if what we're saying is the upper bound of validity is actually already being compromised in the most minimal parts of pre-processing. So we would expect to see a literature that's going to find pretty marked differences with respect to findings on individual differences if we're saying that at the beginning the data is being brought down in reliability. So and also then it depends on what representation you're using. So I guess the good thing is the 200 parcellation unit representation, well, that is more robust to these concerns than the 600 or 1,000. But it also forces you to the thought of, are we really going to keep representing the brain with 200 units? And even the 200 unit, if you look at some pairings of pipelines, it goes down pretty far. Now, dparfs is definitely not in any way inferior to these other pipelines. Actually, it's quite excellent in numerous ways. But it is MATLAB based and relies on routines more distinct because it's SPM based. So was not necessarily surprising for us to see that dparfs wound up having lower reliability, or in a pipeline agreement, I should say. ABCD, that one there is a feature that it defaulted to BB-reg being off, where the other ones were running BB-reg. If it winds up matching up better if one does that. But this becomes this whole game that we start playing of figuring out, what does it mean? And we're like, well, is it part of the brain, or is this a simple, easy thing to figure out? Is it just some network? No, that wasn't the case. So it wasn't like we're just saying this one network is more or less. So then we became this game of, okay, maybe it's just the data. Maybe it's because we're using this data from HNU. So what we did is we went and took healthy brain network data, and we took a cohort with low motion and high motion, because maybe it's head motion, because that's what imagers always worry about. But when you look at the low motion data, sort of high quality data and healthy brain network, and the healthy brain network data is now multiband data and 10 minutes of multiband. So it's more modern imaging compared to the single band. Same problem. And high versus low motion data. I mean, it definitely doesn't solve the problem to use low motion data. The high motion data, I mean, it's either way you go, you have problems here. So it's not about the specific data set we chose. It's not about the specific single band versus multi-band. And across the varying representations, it's all pretty consistent. So that made us feel pretty good about that part. Not happy about the findings. So then comes the part of, well, but doesn't matter. Let's try to put this in context. So that's where we now start looking at the retest data. So this is where you say same subject, same pipeline, same exact scans, same pipeline versus same exact scans, same exact subjects, but different time points. So test, retest. So what do you wind up finding? Well, same pipelines with the same exact data did really well. Encouraging. These are interclass correlation coefficients you're seeing here. So the edges, ICCs. Different pipelines with the same subjects and the same exact scans. This is basically showing you what I've already shown you up here. Marked variation. But what happens when it's the same subjects, but different scans being fed to each pipeline? So pipeline A has time point 1, pipeline B gets time point 2, same subject or same set of subjects. Well, all of a sudden, you no longer appreciate pipeline differences. Not well. But then, of course, come the question of why. Actually, we point here for the pipeline differences. Here, with this, if it's the same exact pipeline being received, receiving the 2 time points, if you look, mean ICC is probably like 0.3 or so. That sounds like what's been reported in the literature. If you just took the average, if you go from 10 minutes to 30 minutes to 50 minutes, you see it goes up above 0.7 for the mean. So this is just exactly what I've shown you before. So it's very sensible from that perspective. Increase the quantity of data per subject. You're seeing an improvement in ICC, replicates the literature well. Look at the different pipelines. With only 10 minutes of data, you really don't have very appreciable pipeline-related differences. Start increasing the amount of data present, and the pipeline differences become more robust. So that's really, in my way of thinking about it, is that means that there is pipeline-related variation, but it's trumped by variation associated with sampling data on 2 different time points. So to test, retest reliability of data, which has been a major holdback in the literature. But as we improve the imaging quality by increasing the amount of data per subject, look what happens. Now the pipelines become the new upper bound on reliability. So I guess the optimistic way of thinking about this is the pipeline-related variation has not probably mattered so much in the literature because the data samples we're using are like 5 to 10 minutes. And they are just, you already have a ceiling being set by the data. But as you increase the quantity of data per subject, which if you think about it, ABCD, HCP, Healthy Brain Network, all these studies have been doing in the last 5-10 years, you're going to start hitting this reality, which is your pipeline related variation. And then if you look at, so scan duration in my mind was like the first checkpoint. And, the nice thing is the picture is very sensible. It's very copacetic. Everything we've known coming into the study, it's just not necessarily what we wanted to hear. Effective global signal regression. Well, when it comes to global signal regression, the realities there wind up being that just like we know from the literature, whether you did GSR or no GSR, you could be highly reliable with yourself. Doing no GSR versus GSR on the same data in the same pipeline, really bad idea. Like that variation associated with whether you did global signal regression is quite pronounced. which again, in the literature where for a long time, half the studies did GSR, the other half didn't. That means that that processing step alone was a huge determinant of the kind of variation you're going to get across studies. Now, from the perspective of pipelines, you can see here the no GSR versus GSR really trumps most of the pipeline differences, at least relative to what you see here when you've matched pipelines on, you know, on whether or not they did GSR or no GSR to follow. Then comes same subject, different scans. So this is our test retest data. I guess the good news is it doesn't matter so much because the quality of the data becomes a determinant again. Low quality, you know, it's if you make the match, if you match or mismatch, it's all about the pipeline differences are most appreciable here. See that GSR versus GSR? If you have a mismatch over here, it's not particularly notable. But again, that's not good. It's just saying that major decisions or major determinants in the literature are probably around the quality of the data from scan duration and whether or not we're consistently looking at the same phenomena by whether or not we did GSR. So the minimal pre-processing pipeline differences, arguably, they're appreciable, but they're appreciable more in the future as we improve the quality of data and we create greater consistency in what we do with the data afterwards, like whether or not we apply methods like GSR versus not. Here, you know, one of the things going back to validity, here what we did is prediction of sex based upon the scans. And what we found is, on the one hand, the data from different pipelines will give you appreciable levels of performance. But what happens is the specific features, if you look at feature importance in your model, it's not consistent. So what does that mean? It means we could all get studies that look like we're performing just as well at prediction and predictive validity, but actually the feature weights will vary appreciably, which if you think of Stephen Struthers and the whole N-pairs framework, the idea was you need to think of both aspects, the weights and the outputs. And this here is, so for people who want to do brain-wide association studies and so forth, they might report similar levels of findings, but the actual specific regions and so forth being implicated are probably varying more than what's being desired with respect to the processing pipelines. And then to satisfy one of the reviewers who just would not stop on this, here's pipelines with interlobe, with low interpipeline agreement have notably lower similarity among features than pipelines with high levels of interpipeline agreement. Because again, we know reliability is bounding validity. And so when you have low interpipeline agreement or reliability, there's no reason to expect that your feature weights or the features you're finding are going to be similar, even if the overall performance of a model looks comparable. So we then spent a lot of time arguing about where these differences come from. And we went through everything. This is a nice version of a leaderboard we were using in an optimization part of our process. Early on, it did not look, the numbers were not this good. But what we were doing is going through and taking different pipelines and thinking this through with respect to, you know, we looked at correlation, the spatial correlation, anatomical masks, you know, again, dice coefficients, looking at the motion parameters, looking at the anatomical, looking at the functional in M&I space, you know, basically going through each piece, looking through and asking about every aspect, each one of the intermediates, and asking, I'm sorry, my voice is really breaking, but I apologize about that. But really with each one asking when these pipelines diverge or not, and going through that question. Here is the example of after we went through a process of harmonizing CPAC, building in all the functionality needed, configurability needed to have a high level of agreement with fMRI prep, the board looks good. It makes you feel good about things. But that's after we sat there and we did this with each of the packages, going through and working with the teams to identify at each step what the differences are and what matters, what doesn't. And this here is example of one, this I just put here as an example. We even went through going through who uses FSL McFlirt versus AFNI 3D Valreg. We sunk a lot of time on this. And this is an example of something that really does not matter at all. Because I sat there and looked at, is it the at the specific algorithm used, decisions about the reference being used, one pass versus two pass. We spent a lot of time and we could get differences to look pretty robust, like the kind of thing you're seeing here. And you could say, oh, that's very scary. But then what we wound up finding is it's actually driven by when you have very low motion. Yes, your parameters will vary, but because there's just about nothing. When you have high motion, then everyone looks the same. And in practice, it doesn't matter at all in the data. But what we did do is we went through this process. We said, fine, let's take large scale steps, the key steps: denoising, brain extraction, anatomical registration, despiking, fold mask generation, and co-registration, and vary them one switch at a time, going when we're looking at taking a pipeline, we replicate all the pipelines in CPAC. Once we did that, we were able to switch from one pipeline to the other, one step, one at a time. So we could figure out, is there some single step that matters so much? And so we created this harmonized space, and then in that space, we flipped the knob, so to speak. And the answer winds up being, it depends. It depends what pair of pipelines you're looking at as to what matters or what doesn't. So in one case, anatomical registration matters a lot and frequently does. But in other cases, it's the brain mask that's mattering more. You know, you wind up being that the source of variation between any given pair of pipelines can vary depending on what specific pipelines you're looking at. So, you know, and at different moments, we've had different conclusions in that process. And you know, and then it was really quite a process to get to a point where we really could trust what we were looking at. But the answer winds up being somewhat unsatisfying in that you need to think about everything, because depending on where you're looking, which pipeline set, it could matter. On the flip side, the good thing was actually, and I skipped one figure, which I apologize for. I'm not sure what happened to it. The pipelines, the good thing is you can achieve 0.9 and higher for across all the harmonized pipelines. So that part's great, but it's a lot of work and it doesn't give you a fully satisfying answer. So you could come back to, great, so we've established pipelines differ. We've established that we could make some pipelines so highly configurable to figure out why they differ, but that the specific steps will vary. So should we have just used one pipeline, a one-click pipeline in this in order to solve the problem? So there, what we did is we looked at fMRI prep, and we looked at one of the first differences that could exist off the top. There's two differences that emerged immediately. One was the fact that they write out by default in the resolution of native space. And number two is that fMRI prep used the 2009 MNI Atlas, not the 2006. Sorry, the template, which, out of fairness, anyone that looks at those two templates would be tempted to because it looks really good. But doesn't matter. So we went and just took fMRI prep. And actually, we first did this in the CPAC version of fMRI prep. And then I looked at our team and I was like, did one of you screw this up? So we went and replicated it in true fMRI prep. If you go and vary the Atlas, the template that's used, depending on 2006 versus 2009, and the write out resolution, look at what you create. Same subject, same data. You wind up compromising significantly. Not surprising if you look at those templates differ pretty substantially. They're both MNI, but the resolution of the template is quite, you know, they're visually quite striking. And also the assumptions about the write out also matter. So it was an interesting exercise to show that even if we say, no, what we're going to do is just constrict the space, the knobs within a single pipeline can also matter. And this is particularly interesting because most fMRI prep was the only one using 2009. All the other pipelines were using 2006. And it's also the only one that was writing out at native resolution. So for us, this was the interesting learning point. Now, it doesn't mean they're wrong for using 2009. Like I said, it's a really nice looking template. But the point is, it will have implications. So we always need to be thinking about these things. We always need to go through this process of doubling back to figure out why. And here's looking at voxel-wise time series correlations, just to give an idea of how things can wind up getting compromised. You're looking at 0.78. Whether or not this matters, the answer also could depend on what specific analyses you're doing with your data. But the bottom line is it has to all be thought through. So for how to move forward, there was a few thoughts. So one, and this here, Greg Kerr is taking the lead. Damien Fair and myself had started this some years ago, and Greg has really been the one to try to run forward with this. Here's a recent paper or a commentary written. One is to try to create more alignment between the pipeline builders. Not to say that anyone's right or wrong, but to think through more about standards, to think more about shared shared data sets used for benchmarking, thinking through more of even just going through and talking through the terminologies. Greg has run a whole series of different hackathons where they've gone through and went through the process of rating different packages based upon the documentation and seeing just how clear documentation is or not, which is definitely a humbling process, including for our team. I did not love it when they evaluated our documentation, but it's also a helpful process. But really, and I think the figure here shows it nicely, where it's coding practices, testing, benchmark data sets. Oops. Sorry. Terminology and documentation, everything matters. And so to the degree that we could increase harmonization, it doesn't mean we all have to do the same thing, but we at least need to be able to have reference data sets, reference pipelines, standards for documentation, so that we can put the pieces together. And there also needs to be more rigorous testing. When we look at changes and key steps, we always have to ask the question, does it matter? And that's a very unappealing thing to do when you're going to review process for grants. Reviewers don't take kindly to that. Anyone that ever tried writing a grant on reliability probably knows that it's not an easy thing. I personally have failed now 4 times. I've written grants on reliability, and worst scores I've ever gotten on grants, because a lot of folks just don't think it matters. It's much easier to talk about the newest of phenomena or some effect than it is to think about reliability. And what one other way of thinking about it, and this here is Greg Kerr's work, and he has actually a piece that'll be coming out sometime in the next several months in Nature Communications, which we'll review. Another way of thinking about it is maybe the variation is not all bad. Greg's argument has been, and this here is some of his work with Tristan Gothard and Alan Evans, but this has really he's been growing this in a number of directions, is maybe to actually leverage the variation across pipelines to actually improve discovery. So to sit there and use the variation as a way to overcome some of the bias that exists in the data, especially when you don't have a ground truth. And so that's where you can start saying, can we take the pipelines and look for ensemble? Can you ensemble the pipelines? Can you look for knocking out some of what does not generalize? And that might be specific to an individual pipeline. And Greg right now has been blowing this out to a very high number of pipelines built across a number of packages. But it's in the middle of all this. On the one hand, there's clearly a value for standardization, a value for reference data sets, benchmarks, all these things. But there's also an opportunity potentially, which is really to think through, can we leverage the variation across different pipelines in a way that could be meaningfully used to improve biomarker discovery, especially when it's a phenomenon where we don't have a true gold standard, which their gold standard for the brain, I think that we could all agree is going to be elusive for quite some time. So given the time, I will finish up on this one here, and also my voice. but I do think I hope that this doesn't come across as a gloomy message when we talk about the variation in the pipelines. And definitely, this paper was never meant to cause any major stir of fear. Instead, I think it's more intended to try to inspire us to think through how to overcome issues with respect to unintended variation, how to also realize that these issues need to be addressed in the going forward, because the data quality is getting really good. We're learning how to acquire high quality data and how to appropriately sample. And it's going to matter more, these little decisions that we take for granted and or the pipelines that we just don't want to think about, the minimal pre-processing. I didn't even get near nuisance regression and the many decisions there in this book other than global signal regression. But I think that part there, I think, is an important wake up as we move forward. And at the same time, it's an opportunity. And that's why I think it's good to end with Greg's slide here. You know, really thinking about, can we leverage that variation to move the field forward in ways we might not have thought of otherwise? On that, I'll finish up.
Well, that's a tour de force. Very interesting. I know there may be folks with some questions, so I'll put that out to the group for questions that folks may have.
Hi, Mike. Do you hear me?
JJB, hey, I got you.
Super cool. I didn't realize how much you've been doing in that space for the last 5 years, 10 years. I mean, I knew some of it, but not all of it. I feel like I haven't done my homework on that. I don't know what you think is the most important thing to do now. Is it still advocating and thinking of the grants that don't go through because the impact is not important, or is it? I mean, I know you're going to say all of it, but if you have to choose, is it to develop platforms that enable assessing those things? Is it to work with the editors and journals to again raise the consciousness, but also raise the threshold of hey, you're publishing that paper with one pipeline, can you try with a couple of others to see whether that's robust? Is it? Yeah. What's your take on the key?
Yeah, no, it's a fair question.
Things to do.
I mean, my bias is I do think it's important to at least push more the idea of testing data with multiple pipelines. And, but the question is, how far do you take that? I know CPAC, when we started, back in 2011, we started CPAC, and I happened to have Arno Klein and Satra Ghosh visiting at the time. And Arno had just published the paper where he compared the different registration algorithms. And that I thought that to me was very impactful. It's like standard Arno thinking ahead and really running with something. And at the time, Satra, I looked at, there was NiPipe, and he was telling me that it had iterables in NiPipe. So when I looked at iterables, it's in there, and then you got Arno pointing out the value of comparing everything. One of the things that I'd also been suffering for about 3 or 4 years at that point, too, was fighting over global signal regression, different corrections also for how to denoise with respect to motion. Do you scrub? Do you despike? And especially with the scrubbing and despiking, it just felt like every paper we're winding up doing with and without scrubbing, with and without GSR, with and without. So that's why CPAC, we jumped onto NiPipe at the time and made it where you could iterate over each of the many, steps in the pre-processing pipeline. And so back then, I always had the idea of having more of a plethora of pipelines and having the package make it where you could generate them quite easily. One of the first times I met Greg Kerr was actually, he was working for Josh Vogelstein, and Greg had blown out like 100 and something pipelines in CPAC. And they were looking at reliability across, and that's bound up being their discriminability paper eventually from Eric Bridgeford. And Greg managed to quite readily capture the vision of what we were after then. I think I still believe there's a lot of value. There's also obviously people said, well, what are you gonna do? Cherry pick the pipeline you want? To which I was like, no, you would like to, there's two parts of it. One is to know, here's the pipeline I chose, and I'd like to think I chose it for reasons, and I should be able to explain them and understand why. But I should know, are my findings dependent upon my decisions? That's the part where I do think testing results with more than one pipeline goes a long way. So with CPAC, we always tried to make it easy by building it into the iterables. This whole thing of creating configurability to replicate ABCD, fMRI prep, and CCS, that was part of what almost bordered on being like some sort of Moby Dick style voyage of just being obsessed with how do we get the answer of what differs and why. But in doing that, there is the capability. So there is one way of trying to do it, where one package gives you a high amount of configurability. Greg, I know, has also put a lot of effort with sticks and boutiques and all the different tools that are being built to make it so you could swap things in and out in frameworks, and you could test different pipelines. I think when you look now at a world where you have the bids derivatives, and it's also in bids, it's everything is easier. And like in CPAC now, we make it where you could just ingress from other pipelines, and a number of pipelines have these capabilities now. So I think you do have to ask, why wouldn't you? And if you get Adriana DiMartino, Adriana in a lot of her work has gone through that process of saying what replicates with the same pipeline versus different in certain decisions. Xiaogan Yan, years ago, Xiaogan tortured himself when he was on our team with comparing different pipelines and these kinds of decisions. Not everyone wants their thing to turn into a methods effort, but I do think there is a certain responsibility to be able to say what decisions, at least the most notable ones, seem to matter or not for our findings. Because otherwise you won't have reproducibility in the literature anyway. If you're pretending that data process with global signal regression versus not doesn't matter, and you expect to see comparable findings, you're probably simplifying the problem. And so I think that's where a lot of the wake-up call in this comes, is there is a value, but to your point, we do need to make it easier for people to do this. Because a lot of people, they're not pipeline developers, they don't want to do it. But if we make it easy and teach the responsibility of it, I think they will.
I think, and part of that may actually be what questions people need to ask, because as I'm listening to this, and I just love the detail, even though it's way over my head, because I feel like it explains so many of the things that people see not meshing between one data set versus another. And it honestly reminds me of if we were to go back one generation, so go back 20 years to when people were worrying about this kind of question for the things like co-registration, and a lot of the motion, scanner, field strength, all those different things, and any one of them would throw things off, and those have all improved a lot. And now it seems like people have a little more sense, or they know somebody who knows what questions to ask to start people thinking about that. But as I was listening to your talk, and I'm thinking, okay, so what questions based on this work, which I think is so rich, but at the same time, it is so rich. And therefore, if you're not sure, which questions might one most importantly ask? And it sounds like using multiple pipelines is part of it, but then it's a little bit of, well, do you have to do the experiment first and see what things are in the data, or can you frame it? Is it too soon to be able to do that for people who aren't really in the depths of it yet?
I mean, I think, I guess my argument would be that there should be, well, okay, because there's a few pieces to it. So like,
yeah.
Because the thing is, look, you could get caught up on things like BB-reg, and which really actually matters a lot. And the brain extraction in some of those comparisons of pipelines, that matters a lot. Not everyone's going to sit there and say, I extracted my data with different the brains with different pipelines in order, when they really want to ask something about region X's connectivity and how that relates to maybe autistic traits or something.
Mm-hmm.
So I think maybe part of it is, I guess one thing is, one could argue the data quality is getting better. And so maybe some steps will matter less. And, maybe we have more and more robust brain extraction tools. So I guess one argument is keep updating certain steps that have proved to be problematic. And that's more on the pipeline developers to make sure, you have things like Beast and all these different algorithms that have come out over time where you can keep improving that and maybe get that off people's minds. So that then falls onto the pipeline developers to make sure they've done that work to know how comparable, how robust our findings with our package versus another, depending on a step like brain extraction. When it comes to my global signal regression, that one's more complicated. Because at my global signal regression, A, it's not part of minimal pre-processing. B, it ties into not just artifact, it ties into arousal and brain dynamics. And I think steps like that are much more rich that people really need to be very conscious about why they're doing it or not. So you could say, take these high level things that could have tied directly to what you're looking at, like global signal regression, something that we know relates to arousal, not just artifact. And that you should definitely be varying or know why you're not. And there's an argument for why not. And that also gets into trickier because are you doing a static functional connectivity or dynamic? I would argue for dynamic, you shouldn't. For static, you probably should. But that's very different than my brain extraction, where I could sit there and say, for good measure, run it across a couple of different pipelines, but and to know that none of that matters. But I think that's as far as most people want to go. Does that make sense?
Yep, it does. It does, yeah.
Can I follow up on one thing? I'm still thinking of the the lab that doesn't have that much IT support and things and do you think? I'm thinking of the NIPOPI project here, that's it's more like a specification of how do we organize data processing and the protocol of how to do that and things like that. Is it a good thing to continue those sort of things, or should we just, I don't know, what are the big next steps do you think should happen in terms of the organization of the pipelines and the testing of the pipeline at the level of each data set that small labs will actually try to process, and what's the, because okay, you've got CPAC and 200 pipelines in CPAC and so on. I mean, how many people will actually be able to actually do those things? The answer is very few, and the results that you may get might also, as you previously shown, depends on the type of data that you have. There's plenty of different things that might happen. So there's a seems to be a need to actually have a local way of doing some simple checks, and I don't know. Yeah, what's your, maybe that's more like a public question than anything else. But what is the minimal kind of things that you would expect a researcher acquiring fMRI data, and and what you let's say you review a paper, what are you going to ask to someone?
Well, I guess there's a couple. Yeah, no, I guess there's a couple answers to that. One is, don't use something custom unless you know why you're using it. So at least one could argue, look, if you're using it with fMRI prep, then I at least know fMRI prep's behavior. And so then just use fMRI prep. Don't use in-house software.
If you fMRI prep is going to change with the next version of fMRI prep and all those things, but
and right there becomes a challenge. So then the thing is, should you process it with two pipelines? And the answer could be yes. And look, CPAC, on the one hand, and Greg's Greg's been amazing with what he's done to bring a ton of stability in East CPAC, and he's going through and validating his 100-something pipelines that people can use. But one could say, let's say that CPAC is amazing, works, all this stuff. What if at some point introduces an error into it in some version? You always have a risk of that with any of these pipelines. So there is an argument for a value in tying together, and comparing pipelines with differing from at least a couple vendors or developers, which I think you're seeing that's much more easy now in a world that has BIS derivatives. And I think Greg would probably argue some of the tools that his team is building is making it easier to plug in different pipelines. But I do think, you know, at a certain point, we either need to have tools that make it very easy to do it in a seamless fashion, or people should really use very well vetted tools. And the problem with fMRI prep isn't fMRI prep. The problem with fMRI prep, in my mind, is what comes after fMRI prep. People all then go and glue with their in-house glue. That's one reason why with the CPAC, we've gone more end-to-end, because we've worried about that. Now, BIS derivatives help solve that in part, but still only in part.
Yeah, BIS derivative is very unspecified as far as I can. I mean,
Yeah,
last
oh
time
no,
I have to-
absolutely. It's still,
looked,
yeah,
but,
but it helps take away some of the glue challenges, but it's still a huge challenge.
Yeah.
But so then, yeah, my thing would be, if you're not going to use multiple pipelines, then make sure you're using one that you're not using anything in-house as much as possible.
avoid the pipeline hacking.
Yeah.
All right, thanks so much, Mike. I don't know.
Yeah.
Any question, guys? And maybe we should let other people. Yeah.
Yeah.
Well, a lot of people are just us, I guess. Maybe. So we should take advantage of Mike's time. We have Mike for ourselves at the moment, almost.
I guess one question is how much of this is tied to functional imaging and how that will translate to other modalities?
Nikhil has been working on the structural imaging aspect of exactly what you've been describing.
And diffusion.
And diffusion. Yeah.
Yeah, I mean, I would say some of the findings that, I mean, several parts of what we found begin with the anatomical. So I mean, I think it's definitely present in even though the example, and it's interesting, the reviewers made us make it resting state or resting connect, you know, imaging. It's broad in my mind. This is true of any imaging, and truthfully, if I went to EEG land, I find a way scarier picture. So I think these are general traps that we all fall into. And with imaging, we all would like to have thought that the brain extraction wouldn't have mattered. And we all, you know, and the reason why we went to the Healthy Brain Network data is it's like, okay, wait, that's a much better looking anatomical, and it's got the multiband. And so this, maybe it's okay there. And then we saw the problem. So I think as much as possible, getting really robust brain extraction is a key for bringing down the contributions on the structural side. But then you have to deal with, you know, does someone do like local denoising or not, and all those other pieces. But the brain extraction and anatomical registration, those two explain a lot of what we found. So I think once we hit really being robust there, and it could be we have very robust solutions for newer data, and you just have to say so much for the old, you know, but maybe not. That's to be seen.
Thanks so much, Mike. Any question? I mean, you have to promise us to come back.
Yeah.
Happy to.
I really would like, you know, like you know, maybe an hour of you know, discussion and showing things and discussion on those things more. But both at the philosophical and the practical levels, I think you know, would be super interesting. So